G'day everyone. On this video we're going to be covering a subject called diffusion. Now diffusion is one of those areas that I think is really not really covered enough when you're going through training as an apprentice and mechanic or whatever field you're looking at in relationship to the mechanical field, because it relates to a huge amount of concepts that are contained within a vehicle or a machine that really you need to have a good understanding of what diffusion is for fuel systems, cooling systems, lubrication systems, because diffusion has got an impact on every one of those areas. So we're going to cover a few videos, probably four different little videos covering a lot of aspects as to where this rate of diffusion has an impact. And we'll start with a really simple one for a start, and that is just showing you how fast molecules are actually moving around, even though you'd consider them to be relatively still. So what I'm going to do is I'm going to firstly, to kick the process underway, in getting some red food colouring and putting the red food colouring into a container of warm water. That water's warm, so we'll inject the food colouring in there. And we're going to do the same thing with the blue. So that container is cold. Both of those containers have been sitting, one in the fridge and the other one's been sitting in a filler with warm water. But we've had them sitting for about 10 minutes, quarter of an hour, I suppose. So they've had time to settle down and get used to this. So there's no currents that are actually being generated through the fact that the containers have been moving. So I'm quite happy about those two containers. Are actually going to give a good outcome at the end of this little segment. But what we are comparing it to, or what we're trying to get our head around, is the fact that when we have a look at a glass of water, and we would expect those molecules inside the glass of water to be still. So in other words, they're not moving. But in real terms, they're actually moving around at a speed of 1,900 kilometers an hour, but that's at 20 degrees Celsius, and that's quite an important thing to remember. At 20 degrees Celsius, each one of those molecules of water is traveling around at 1,900 kilometers an hour. But if it gets warmer, they travel faster. If it gets colder, they travel slower. And that is, we're already seeing that that's becoming quite evident when we're looking at our container of warm water here in comparison to our cold water. What we're doing is measuring and looking at how fast those molecules are moving around continuously, even though a substance like a glass of water you would think is relatively still. The molecules are moving around at an enormous speed. And the collisions they're actually doing is something like, I think it's 10 quadrillion collisions every second. So there's a huge amount of stuff going on in water that you wouldn't really think existed. The second thing we want to have a talk about is evaporation, because it's also got an impact on fuel systems in relationship to the fact that a fuel will only burn the vapors. And what needs to occur before that fuel will actually burn is we need to allow that fuel to change from a liquid into a vapor before it'll actually ignite. And so it's not the burning of the liquid that is burning, it's the burning of the vapor. So just the same way, evaporation has got another really, look, I thought the water had to be at 100 degrees Celsius before it would boil. So how come I can actually sit a glass on a bench and come back 2 days later and there's some of that water missing? What's going on there? And what is going on is the fact that each one of those molecules of water that is moving around at 1900 kilometers an hour is going to be moving around, but some of that is actually going to be coming up to the surface. When it hits the surface, it's going to escape. And so that escaping those molecules are traveling so fast, faster than the speed of sound, they hit the water and escape into the atmosphere. And that's what evaporation is. It's not reliant necessarily on anything more than the fact that those molecules are moving around. We'll do another experiment relating to the same thing also, and what I'm going to do is put some ice cubes in the freezer and measure how much ice cubes lose in terms of their mass over a given amount of days. But to kick the process off, we would just want to cover some simplistic stuff. Well, it's all going to be pretty simplistic anyway, but it's really important to understand the impact that this rate of diffusion has got on a variety of different areas. Now, we can see already that we've got a whole heap of streaky lines coming down on our cold side, and already we've got a huge amount of distribution of that even distribution of food colouring with our red food molecules, or our red food colouring. And the reason for that is the fact that the molecules are moving around, but they move around at a speed that is relevant to their temperature. So the rate of diffusion is proportional in so many different factors, and that is, one of them is temperature. So when you're measuring the temperature of a fluid, and remembering that fluid is either a liquid or a gas, we're measuring of the rate of how many or how fast those molecules are actually moving around. What also has an impact in relationship to the rate of diffusion is the fact that you've got the capacity for a fluid to actually thin out or thicken up based on the rate of diffusion. So we all know that oil becomes thicker when it gets colder. It gets thinner as it gets warmer. So not only is the rate of diffusion proportional to its temperature, but it's also proportional to its viscosity. So we know that when you actually heat water up, heat any fluid up, even water actually, water also actually gets thinner as it gets hotter. And so when you are heating up oil, and as a really good example, inside a vehicle or a machine, the oil heating up, it allows it becomes thinner, and therefore it flows around the components inside the transmission, diff, engine, whatever it might be, faster. And that's where the other side of the rate of diffusion has an impact, and we're going to be doing experiments on that. The other one area that we're going to be looking at is the flammability range of fuels. We know that petrol will ignite at a relatively low temperature, minus 40 degrees Celsius. But if you get a fluid such as diesel, or a fuel such as diesel, it's not going to ignite until it gets to a much higher temperature. And we'll go through these factors when we're going through the experiments that we're going to cover. So that's covering the basic concept of what we're going to try to achieve over the next 2 or 3 videos, but they're all related to the rate of diffusion. Another example of where diffusion plays a really important part is the burning of fuels. So when you're looking at fuel and you're looking at going to do a safety course when it comes down to fuels, they talk about the fire triangle on a regular basis. Now, the 3 things that will allow a fire to exist in the first place is going to be the fuel itself. We need to have oxygen to be able to support that fire, but we also need to have heat. Now, heat generally is the one that is least understood. We know that if the fire is happening, the firefighters have got one of 3 things they can eliminate in order to be able to get rid of that fire. One, they can extinguish it by taking the oxygen away. Another one is simply by turning the fuel off in the first place. But the third one is heat, and heat is generally the one that is least understood. But it's one that plays a huge and important part, because fuel will not burn in the form of a liquid. It's got to turn into a vapor before it'll ignite. When we get into our series of videos on firewood, or how wood burns and fire itself, that's a really important factor to understand, because a fire will not burn without changing that wood from a solid directly into a gas. There's no liquid phase taken into account. It changes directly from a solid into a gas. Now, in the form of liquid fuels, such as we're using diesel as an example, we can actually try and set light to that diesel, and we're going to be doing this experiment next. But when we try to set fire to that diesel, it will not ignite. It's got to be a temperature of around about 65 degrees Celsius before it will actually allow that fuel to burn. Then after that, it'll start to accelerate and get stronger and stronger, or more intense. But in its natural state, in its normal temperature of whatever the ambient temperature is at the time, it will not ignite in the presence of a flame. So what we're going to be doing is we're going to be getting setting a pot of water, a pot of diesel, onto a fire, and then we're going to add a flame. And after we add that flame, we're now going to increase the temperature of that diesel, and we're going to continuously try to put a lighter in to set fire to that diesel, and it won't burn until we get to that 65 degrees Celsius. So the difference being is the fact that the molecules of diesel that are rattling around inside are rattling around just the same way as our water. In other words, the rate of diffusion is proportional to temperature. As that whole fire starts to get, or the diesel starts to get warmer and warmer, now the rate of acceleration of those molecules increases. Therefore, the rate of evaporation is proportional to the rate of diffusion. So the greater the rate of those molecules moving around will allow for a greater degree of evaporation of that fuel taking off the surface. When that gets warm enough and to the point where it gets to 65 degrees Celsius, and then we put our match to the top of the fire, or whatever we're going to light it with, that will then start burning, and it will maintain an even distribution of flame because the rate of those molecules moving is continuously feeding that fire. But, and this is the next part of the process on our experiment, is the fact that after that fuel is on fire, we're then going to take or turn the fire off, or turn the fuel off. Then we're going to take our pot and we're going to set that pot into a container of cold water. So I'm going to stir the diesel while it's on fire, while that whole pot is now sitting in a container of water. And in doing so, that heat within the fire itself is now being lost through to the cold water. And in doing so, the temperature is going to get lower and lower and lower until we get to that magical 65 degrees Celsius or thereabouts. And then what we're going to do is we're going to find the intensity of that fire become less and less and less until that fire goes out. And that's where the third part of that saying comes from. Get rid of the fuel, we can put the fire out. Get rid of the oxygen, we can put the fire out. If we remove the heat, we can also put the fire out. Now, you may have seen on oil refinery fires where the firemen are actually out there with their fire trucks trying to not put the fire out initially. What they're trying to do is on the side of their large tanks, they're squirting water onto the side of those tanks. Not to try and put the fire out, but to reduce the rate of diffusion inside those large tanks until the experts can come on board, and then they can work out a way that can actually put that fire out. But it's reducing the intensity of the fire because they're removing some of that heat, therefore reducing the rate of diffusion. So that's going to be our next little experiment.